Are there any questions?
How was your weekend?
It's okay. Not as productive as it should have been.
Same.
But I still do have stuff to return. I probably should set my alarm so that I remember to actually return it. Even better, I'm recording this. Because this makes good video. Any other questions besides how things were on the weekend? Let's go through the look on the ramp problem. And then we'll move on to chapter 6. Thinking the original problem, this was a book and a cup or something like that, but they're just two messes. Let's make this 5 kilograms, that 3 kilograms. The initial velocity is up at, let's say 7 meters per second. Anything else I need to do here? Ideal rope and pulley. So the question is, how far up the ramp will the 5 kilogram mass go before it stops? Oh, friction. I left friction out of it. I'll go with our traditional 4 and omega wedged. So how far up the ramp? And then the follow-up question is, will it slide back down? So the first thing is we need to look at it from trying to figure out what the acceleration is. So let's go through the steps. What's the first thing that we're supposed to do?
Draw the thing.
Okay.
So I've got 5 kilogram mass here, and I've got 3 kilograms. I'll just put 5 there and a 3 there. We have the rope, and then we have ground.
Now what? Are you going to make Logan do all of the work?
Identify your forces.
Okay, force diagram. So let's go to our checklist. F, Tom. All right, what force is acting on what object and in which direction? That is closest to stone.
weight is down on 3 and then up on earth, or the ground or whatever.
So I have weight, sub 3, weight sub 3. All right, one down.
Is it not any tension on the rope?
There is tension on the rope.
So the bottom would be down, I think.
On the rope?
Mm-hmm. The top of it would be upright.
And then up on the third, the 3 kilogram box, and down the 5 kilogram box.
All right, tension's done. I have only one rope, we took care of both ends. We've got at least one more gravitational force pair, or one more weight pair. We've got 2 normal force pairs, and we got a friction pair to go. All right. That is closest to the top, so take it.
So I'm thinking of the friction on the 5 kilogram box.
Okay.
Because it's moving upwards, and it's going back down.
We're just worried about going up at the moment.
Okay, so the friction force on the box would be going this way. And then up on the ramp.
All right, friction is done. 3 more pairs to go. The nearest person who hasn't said anything yet. That would be Natalie.
Normal force down on 5 kilogram and up on the ramp,
Normal force down on the 5
or
kilogram?
like towards the ramp.
So normal force is pulling them together?
Or
Normal force is a support force. It keeps one object from going through another. It tries to keep them apart. It's the bouncer of the group. When it breaks up the fight.
So would it not be going?
The normal force goes the other direction. Normal force pair will go away from each other. And I think at this point, we're left with Yolanda, the only voice I have not heard yet. There's one normal force pair, there's one weight pair. Take a guess, the worst that happens is you're wrong. Up on the what? On the 3? What is the 3 touching? In order for there to be normal force, there has to be 2 objects touching each other. The only thing 3 is touching is the rope, and we've already counted for that in tension. But there are 2 objects that are still touching that we have not identified yet.
Would there be something on the rope in the pulley?
Yeah, that's the other one.
Which way is it going on the rope? Straight up,
Well, to the right.
up and to the right. Yolanda, what were you about to say? That way? It's gonna be touching the pulley in this region right here. So it's gonna have to be somewhere in that range. So why is a pulley? Why is a pulley? And the last pair, maybe now do this. Dominic. The last force pair that has not been identified yet.
Do we wait from the box 3? Or box 5, wasn't it?
Yeah.
Wait for box 5.
Wait 5. Wait 5. All right, there we go. And having done this a number of years, and when I open it up, yeah, we got one of the weights very quickly, but the other weight, I'm just surprised that weight is not the first thing that every person thinks of. It's as if we don't all think alike. Huh? Yes, Logan.
The box is only, like initially was only going this way because we said so.
Yes.
Okay.
Yeah. Somewhere there we go. I recorded some of you present yesterday. All right, so force diagram done. Now what? All right, that's work. Solid starting to help. Done the fourth
Identify
diagram.
acceleration,
Pardon?
identify acceleration.
Or direction of acceleration. All right, in which direction is the 5 kilogram mass accelerating?
Up to the right.
So it's accelerating in the direction it's moving.
Down to the left.
It's accelerating opposite the direction it's moving.
Oh, never mind. I think he's right.
Up to the right.
So if acceleration and velocity are in the same direction, what's an object doing?
Going in.
I heard somebody say it, I think. There were multiple voices, almost in unison. It was really good.
Speeding up.
Yeah, it is speeding up. So in this situation, if I have a box that is moving up the ramp, when we come into the picture, it's already moving up the ramp. Do you believe it's going to speed up as it goes up the ramp? It's not my experience that it would speed up. So if it's going to slow down, what do you know about the direction of acceleration? Aaron? If it's slowing down, direction of acceleration? How about this? If it's slowing down, what can you tell me about the relationship between the direction of acceleration and direction of velocity? All right, anyone?
It's down to the right. I mean, down to the left.
And you said
Both are negative?
not both are negative.
Velocity is positive and then up to the right, and then acceleration is negative.
Okay, they're gonna be opposite signs, however you want to define positive. Stone just established, he wants to make that positive. But acceleration would indeed be back down the ramp. Because the arrow points the direction. And therefore, what is the direction of acceleration of box 3?
Straight down.
It's slowing down. The acceleration is opposite direction. And if I look at the forces acting on the 5 kilogram mass, there is no force acting up the ramp. It cannot be accelerating up the ramp because I have no forces, assuming that this is right, I have no forces going in that direction. Therefore, acceleration cannot be in that direction. Now, if you're thinking that, well, it's moving up the ramp, so something must be pushing it, that's a false assumption. It's moving up the ramp for some reason, we don't know why. How it got there is irrelevant. What we care about is what's happening at that moment. And what's gonna happen in the future. All right, so acceleration, done. Now what? Okay, so how do we want to do this coordinate system? Are we gonna go with Stone's first suggestion of up the ramp is positive? Or do we want to say, Stone, not today?
So go stones.
You're gonna go with Stone's?
It just seems easier than what we've learned to do.
All right, so up the ramp. And so we'll call that I5 hat.
Up to the left.
Is,
Positive.
okay, J5 hat. What about for the 3 kilogram mass?
Straight down?
You wanna make that positive?
No, they're positive, no.
Negative.
Go down to be negative. So up is positive.
Yeah.
Okay. Either way. I'll call that I3 hat. All right, so done. If you want a J3 hat, that's fine, but there are no forces in that. The only forces acting on 3 are vertical, so I only need a vertical axis there. I do recommend that if they're not exactly the same direction, but this thing is moving like that. So if we're making that positive, it's beneficial to make that one positive also. However, not crucial, just have to put the minus sign in the right spot. Now what?
Decomposition.
Okay. Do we need to break either of these up?
No.
Why not?
Wait.
Why not?
Because they're not like different from the axes.
Okay. They're parallel or anti-parallel to the axis. Okay, what about here? Do we have to break these up?
Yes.
What?
Weight.
Yeah. So at this point, I'm only looking at the 2 masses. Because my equations of motion have a mass in it. Those are the ones I care about. And we assume that the planet is not moving. All right, where we go? If this angle down here is theta, so we're gonna break weight up into part of it going down the ramp and part of it going into the ramp. So I've got friction acting back this way, I have tension acting back this way, I've got normal force acting this way. And so I have part of my weight acting into the ramp and part of my weight acting down the ramp. Well, I know one of them is going to be sine of theta, one's going to be cosine of theta. Which one's which?
Down to the right would be cosine, down to the left would be sine.
Down to the right, so cosine and sine?
Yeah.
Yeah. So this is weight 5 cosine theta. Weight 5 sine theta. You just remember it, or you did it in your head, or?
It looked like the other examples we've done before.
Okay.
I had a 50-50 guess.
I'm hoping it will eventually not be a guess anymore, but wherever you are right now.
The ones with the normal force was normally cosine.
If you're given the angle versus the horizontal, then yes. And that one stays as is. So I'm making the claim that we can take weight out of it and replace it by these two, because if I add those two vectors together, that adds up to weight. Now what?
Equations.
All right, so we've got equations. How many will there be? There we go. Yeah, I'll have two equations here, or one equation here. So I'll have an I5 hat, a J5 hat, and an I3 hat. Please, share. All right, I'll go to pointing. That is stone. Rough axes here.
I3 hat would be FT minus weight 3 is equal to mass times acceleration.
All right, let's take a moment here. He could be right, or he's made a mistake.